Okay. Okay, folks, it is that time of the day. So I am going to go ahead and get started. I will be flipping back and forth between all of my, between my my iPad and my computer as far as what I'm showing you, because I do have some videos I want to show you. So I will be flipping back and forth. So in lab today, what we will be talking about is we will be discussing VSEPR theory, VB theory, molecule polarity, and sigma and pi bonds. The handout that I keep referring to this week that you got on Tuesday, it is going to be a very useful handout with respect to the information that I will be going over with today as well. Now, before we get started, before I actually get into the very first video, I want to introduce this concept of VSEPR theory. VSEPR stands for valence shell electron pair repulsion. Where VSEPR literally comes from the first letter of each word. Now, before we get into, oh, sorry about that. Thank you for letting me know, Marissa. Let's try doing this again. There we go. Okay, so we're going to be focusing on these particular topics today. Again, VSEPR theory stands for valence shell electron pair repulsion. Now, if we think about valence shell electron pair repulsion, let's really break that apart. When we were developing Lewis dot structures, in step number 1, we were determining the number of valence electrons. We would go, well, carbon is in group 14, the last digit is 4, so it has 4 valence electrons. So chlorine is in group 17, the last digit is a 7, so it has 7 valence electrons. So when we were developing the Lewis structures, we were specifically adding up those valence electrons. As we developed the Lewis structures, those valence electrons were placed in pairs, whether that pair was in the form of a bond or whether that pair was in form of the lone pair. So really, the only term that is completely new here is this concept of repulsion. And what you have to remember is electrons are negatively charged subatomic particles. And when you bring negatively charged subatomic particles near other negatively charged subatomic particles, they will repel one another because of the fact that they have like charges. So what we're doing is we're looking at this repulsion that occurs between our bonds and our lone pairs in the molecule. Now, before I get into too much detail, or before I show you the video, the next thing I wanted to quickly mention is that we will be talking about two types of geometries. The very first geometry that we're going to talk about is going to be the electron geometry. The electron geometry is the geometry that is based on all the valence electrons on the central atom. When I say all valence electrons, I am going to be talking about the bonding electrons as well as the non-bonding electrons or lone pairs. The second type that we will talk about is going to be the molecular geometry. And the molecular geometry is the geometry that results from evaluating just the bonding pairs or bonding groups within the electron geometry. And once we get to working problems, you will see how I take this into account. The first thing I'll do is I will take the Lewis structure and I'll develop the electron geometry. And then from the electron geometry, I will look closer and develop the molecular geometry from that. So we'll talk about that more. Now, I will let you know up front, I'm going to show you some videos. We're going to talk about the key points in the videos. I'm going to show you multiple videos. So up front, I'm going to inundate you with information. Then on the back half of today, the goal is to actually take that information and work through some problems so that you can see how all of that information can be pared down to create the answers to the molecular geometry, the hybridization of the central atoms, the polarity of the molecule, and the sigma and pi bonds. So the first, whoops, let's see, where do I want to go? I'm going to go here. So the first thing I'm going to do is I am going to share the video. As I can find everything again. So you may recognize this current location. This current location is this week's folder in your Blackboard. And the first two videos that I'm going to show you are going to be found in the video lectures folder. The first one is the VSEPR theory.
Chemists use valence shell electron pair repulsion, or VSEPR theory, to account for the shapes of molecules. The theory is based on the idea that like charges repel each other until repulsions are minimized. The like charges in this case are the groups of valence electrons around a central atom in a molecule or ion. We'll represent them as bars attached to a sphere and show the electrostatic repulsions as yellow arrows of varying width. The simplest case has two negative groups around a central atom. At any angle less than 180 degrees, electrostatic repulsions push the bars apart. Repulsions are minimized when the bars attain a linear arrangement. Electron groups can be single bonds, as in gaseous beryllium fluoride, double bonds, as in carbon disulfide, triple bonds, as in hydrogen cyanide, or, as you will see shortly, lone pairs. Three negative groups attached to a central atom attain minimal repulsions in the trigonal planar arrangement, which has an ideal bond angle of 120 degrees. We observe this angle in molecules with three identical groups, such as boron trifluoride and sulfur trioxide. Molecular shape is determined by the positions of atoms, not electron pairs. Therefore, if one of the electron groups is a lone pair, the molecular shape is not trigonal planar, but bent or V-shaped. Since a lone pair is held by only one nucleus, it is less confined in space and exerts greater repulsions on nearby bonding pairs. As a result, the bond angle is less than 120 degrees, as you can see in this model of ozone. Four electron groups around a central atom attain minimal repulsions in a tetrahedral arrangement, which has an ideal bond angle of 109.5 degrees. The tetrahedral shape is very common, especially in organic molecules. An example is methane, the simplest hydrocarbon. With one of the four electron groups, a lone pair, the shape is trigonal pyramidal. Since a lone pair exerts greater repulsions than a bonding pair, the bond angle is less than 109.5 degrees. Ammonia is a common molecule with this shape. Its bond angle is 107.3 degrees. When two of the four groups are lone pairs, the molecule has a bent or V shape. Two lone pairs exert greater repulsions than one, so the bond angle is reduced even further. Water, for example, has a bond angle of only 104.5 degrees. Four electron pairs fill the valence level of a period 2 atom, but one from period 3 or higher can use d orbitals to expand its valence level and bond to more than 4 atoms. 5 electron groups minimize repulsions when they point to the corners of a trigonal bipyramid. Here we find two ideal bond angles. Equatorial groups lie 120 degrees apart, and axial groups lie 90 degrees away from equatorial groups. When phosphorus reacts with excess fluorine, the trigonal bipyramidal molecules phosphorus pentafluoride forms. Once again, when lone pairs are present, different shapes result. But a lone pair in an axial position creates 3 strong 90-degree axial equatorial repulsions, whereas a lone pair in an equatorial position creates only 2 90-degree repulsions. Therefore, to minimize the number of 90-degree repulsions, lone pairs always occupy equatorial positions. As before, lone pair repulsions reduce all other bond angles. With one lone pair, the object has a seesaw shape. Sulfur tetrafluoride is an example. With 2 lone pairs, the object is T-shaped, and the 2 remaining angles are less than the ideal 90 degrees. Bromine trifluoride is a T-shaped molecule. The final shape in the trigonal bipyramidal arrangement occurs when a third equatorial lone pair repels the axial groups to 180 degrees. The object has a linear shape, as in the case of the triiodide ion. The final common arrangement has 6 electron groups attached to the central atom. Repulsions are minimized when the groups point to the corners of an octahedron and thus lie 90 degrees apart. Sulfur hexafluoride has an octahedral shape. Unlike the trigonal bipyramid, all positions are equivalent in an octahedron. So one lone pair can take any position to give the square pyramidal shape, with all bond angles less than 90 degrees. Iodine pentafluoride has this shape. To minimize repulsions, a second lone pair must lie 180 degrees from the first. The 4 remaining bonding groups are repelled to the ideal 90-degree angle and define the square planar shape. Xenon tetrafluoride, one of the first noble gas compounds to be made, is a square planar molecule. When the atoms in a covalent bond have different electronegativities, the electrons are shared unequally and the bond is polar.
Hold on.
Depending on the molecular shape, polar bonds can give rise to a polar molecule, one with an overall unequal.
Where it's coming from. Okay, so let's get into the key points of that particular video. As soon as I can get the right one. There we go. Okay. So the first key point to this video was that the electrons whether in bonds or as a lone pair, will arrange themselves so as to minimize repulsions. It is this fact that leads to the electron geometry and molecular geometries. Now, when we are working on this, a second key point is that a single bond is considered as one electron group, but so is a double bond. And a triple bond. And finally, so is a lone pair, or in the case of a free radical. This particular piece is going to be important later on. One of the things that I do to try to help you determine the geometry is I help you develop what I consider to be a notation based off of the Lewis structure. And as I'm working on that notation, I take into account that a single bond is just one group and a double bond is just one group, and so on and so forth. Now, the third thing, that was the third key point, was that only the bonding groups are taken into account when describing the molecular geometry. A fourth thing is bond angles. Now, basically, ideal bond angles can be determined based on the electron geometry. But if a lone pair is present, then the bond angle will be less than ideal. The other thing that came out in this particular one is, where do you place lone pairs in molecular geometries? If it is, if let's actually change that molecular to electron. So if the electron geometry is linear, trigonal planar, or tetrahedral, all locations are the same, And it doesn't matter where you put the lone pair. For trigonal bipyramidal, lone pairs must go in the equatorial positions. The reason for this is because the equatorial position, there is greater space. There's more space for those electrons to spread out. And then finally, with respect to the octahedral, it doesn't matter where the first set is placed. But the second one must be 180 from the first. Those were the key points associated with the VSEPR video. And if you look at the packet that I gave you, we'll talk about the first column in greater detail when I start doing some examples, but you'll notice bonding groups, non-bonding groups. You will notice what electron geometry they have, what their electron geometry is called. You will also notice the molecular geometry, what the molecular geometry is called, and then you start getting into the bond angles. So that packet actually does help go through a lot of what we just wrote out in detail. And it will come in useful when we start doing problems later. Okay, so now I'm going to stop share this one, and I am going to get to the second video. Which is not this one. The second one is valence bond theory. And again, I will talk about the, we'll go over some of the key points after the video is over.
Chemists use valence bond theory, and especially the concept of orbital hybridization, to answer a fundamental question. How do the shapes of the molecules we observe arise from the orbitals of the isolated ground state atoms that bond? The hybridization concept proposes that in the molecule, the orbitals of the central atom have mixed mathematically and become hybrid atomic orbitals, new wave functions with different electron densities and spatial orientations. Let's begin with the simplest case and see how the theory accounts for a molecule with a linear shape. A key point to note is that the number of atomic orbitals that mix always equals the number of hybrid orbitals that form. Here, two different atomic orbitals, one 2s and one 2p, mix mathematically to become two identical sp hybrid orbitals, each with one larger and one smaller lobe. The two orbitals face in opposite directions in the atom. For clarity, we'll show hybrid orbitals in this simplified form. First, we'll use box diagrams to depict hybridization and consider the central beryllium atom in the linear molecule BeCl2. The isolated Be atom has filled two s orbital and three empty 2p orbitals. In the process of hybridization, the 2s and one of the 2p's mix and form two sp hybrid orbitals. The two electrons from the 2s become distributed into the sp orbitals, one electron each with parallel spin. The two other 2p orbitals remain empty and unhybridized. Here is the same process in a box diagram that shows orbital shapes. Putting these ideas together, we can imagine the hybridization process for BeCl2 is something like this. The isolated beryllium atom, with its filled 2s and empty 2p's, is shown with the small box diagram above. The chlorines have three 3p orbitals, but will fade out the ones that are not involved in bonding. In the molecule, beryllium has undergone sp hybridization. The half-filled sp hybrid orbitals overlap the half-filled chlorine orbitals to form two BeCl covalent bonds that are 180 degrees apart. From here on, we'll show electrons within orbitals as dots. To account for molecules with a trigonal planar shape, such as boron trifluoride, the model proposes that the ground state boron atom undergoes sp2 hybridization. The filled 2s of the central boron mixes with one half-filled and one empty 2p to become three half-filled sp2 hybrid orbitals. Boron's third 2p remains empty and unhybridized. Here's an orbital depiction of the ground state boron with filled 2s, half-filled 2p, and two empty 2p's. The fluorines have half-filled 2p orbitals. In BF3, the boron atom is hybridized with the three sp2 hybrids pointing to the corners of an equilateral triangle. Boron and fluorine orbitals overlap to form three BF bonds 120 degrees apart. To account for the millions of molecules with tetrahedral shapes, the model proposes that the central atom undergoes sp3 hybridization. For example, in the carbon of methane, the filled 2s, two half-filled 2p's, and empty 2p mix and become four half-filled sp3 hybrid orbitals. The model describes bonding in methane this way. In the molecule, the carbon's four sp3 hybrid orbitals point to the corners of a tetrahedron. The H orbitals overlap them to form four CH bonds that are 109.5 degrees apart. For other shapes within a given electron group arrangement, the model proposes lone pairs in one or more of the hybrid orbitals. For example, the trigonal pyramidal shape of ammonia arises when the 2s and the three 2p's of the central nitrogen mix and become four sp3 hybrid orbitals, one which is filled with a lone pair. Here, we visualize the nitrogen atom undergoing sp3 hybridization. One of the tetrahedrally oriented sp3 hybrids is filled with a lone pair, and the H atoms overlap the other three to form three NH bonds. In the case of water, with its V shape, the model proposes a situation similar to that for ammonia. The 2s orbital of the central O atom mixes with its three 2p's and becomes four sp3 hybrids, but now two of the hybrid orbitals are filled with lone pairs. In the water molecule, the oxygen has undergone sp3 hybridization. Two of the sp3 orbitals are filled with lone pairs, and the H atoms overlap the other two to form two OH bonds. Carbon is most commonly at the center of a tetrahedral grouping of single bonded atoms, but it also occurs at the center of a trigonal planar grouping that includes a double bond. Consider the carbon-carbon double bond in ethylene. Valence bond theory proposes that each carbon undergoes sp2 hybridization. Its filled 2s and two half-filled 2p's mix to become three half-filled sp2 hybrids, and the fourth electron occupies the unhybridized 2p. Let's examine the orbital view and highlight the two ways carbon orbitals overlap to create a double bond. Here, each carbon is undergoing sp2 hybridization. Note how the unhybridized 2p orbitals lie perpendicular to the trigonal plane of sp2 hybrids. The two sp2 orbitals facing each other overlap end to end. The bond they form is called a sigma bond. It is symmetrical along an imaginary line between the nuclei and is not weakened by the rotation of one atom with respect to the other. Now, focus on the two parallel 2p orbitals. By substituting accurate representations of 2p orbitals, you see that they can easily overlap side to side. This results in a pi bond, one that is not symmetrical along the line between the nuclei. Most importantly, it is weakened and in fact breaks by rotation of one atom with respect to the other. Thus, a double bond consists of one sigma and one pi bond. In the ethylene molecule, 4 H atoms overlap the 4 other carbon sp2 orbitals. Recall that in molecules with more than 4 atoms around a central atom, such as phosphorus pentachloride, the central atom utilizes d orbitals to expand its valence level. Hybridization accounts for the shapes of these molecules as well. In the ground state, phosphorus has a filled 3s orbital, 3 half-filled 3p's, and 5 empty 3d's. In PCl5, the 3s, all the 3p's, and one of the 5 3d orbitals mix to form 5 half-filled sp3d hybrid orbitals. The other 4 3d orbitals remain empty and unhybridized. Here is the ground state phosphorus atom with the 4 3d orbitals that remain unhybridized, omitted for easier viewing. We'll move back to see the hybridized p atom in PCl5. The 5 sp3d hybrid orbitals point toward the corners of a trigonal bipyramid, and half-filled 3p orbitals from 5 chlorines overlap them. Sulfur also has an expanded valence level in many of its compounds. In the ground state, it has a filled 3s orbital, 1 filled and 2 half-filled 3p's, and 5 empty 3d's. In the octahedral molecule sulfur hexafluoride, the 3s, all of the 3p, and 2 of the 5 3d orbitals of the central s mix to form 6 half-filled sp3d2 hybrid orbitals. The 3 unhybridized 3d orbitals remain empty. Here you see the isolated sulfur with 3s, 3p, and the 2 3d orbitals that will become hybridized. In SF6, the 6 sp3d2 hybrid orbitals point to the corners of an octahedron, and half-filled 2p orbitals of 6 fluorines have overlapped them.
Hello and welcome to a video about hybrid orbitals,
again.
often called valence bond theory, developed in the 1930s by the great chemist Linus Pauling as a model of bonding to understand the three-dimensional placement of atoms in a molecule, and that is critical to our understanding of the properties that molecules have. In this
Okay. Now, I can go back to stop share. Okay, so let's look at the key points here. Okay, first of all, let's talk about what valence bond theory describes. Valence bond theory describes the hybridization the central atom must undergo in order to obtain the geometries observed. Now, the number of hybrid orbitals is equivalent to the number of atomic orbitals that mathematically combine. What that means is if I combine, say I have the atomic orbitals S and P, and I combine those together mathematically, then I will get out the hybrid orbitals of, I will get out two hybrid orbitals because I put in two atomic orbitals, so I get out two hybrid orbitals. And those hybrid orbitals are sp hybrid orbitals. If I put in one S and I put in two P's, that means I'm going to get out three hybrid orbitals that are called sp2 hybrids. So the third key point comes down to the fact that there will be a maximum of one s orbital, a maximum, good grief, of three p orbitals and a maximum of 5d orbitals that can combine. And the reason for this actually comes back down to quantum numbers. If you'll recall, when L is equal to 0, which means you have an S subshell, then the only possible value for M sub L was 0, which means you only had one possible orbital in the S subshell. For the P, L is equal to 1, which is the P subshell. That means that you could have a -1, a 0, or a 1 for the M sub L. Therefore, you could have 3 orbitals. And then then D, you could have a maximum of 5 orbitals. So basically, this is coming back down to our quantum numbers as to the maximum that we could combine. Here, I only combined one S and I combined one P at the beginning. The next one, I combined one S and 2 Ps. I could continue, but after the third P, if I need another orbital, I would have to bring in the Ds. Now, the fourth point is that the hybridization of the central atom is based on the electron geometry of the molecule. And the last key point that came up in this particular video is that there are 2 types of bonds. Which are called sigma and pi. A sigma bond which I am sorry to say I'm not very good at writing the sigma, but so mine looks like a sideways 6 because it's a lowercase sigma. The sigma bond results from direct overlap of a hybrid orbital with either an atomic orbital or another hybrid orbital. If you're talking about the central atom interacting with an external atom, the overlap will be between a hybrid orbital and an atomic orbital. But if you're talking about the bond between 2 central atoms, then the overlap will be between a hybrid orbital and another hybrid orbital. So it basically depends upon whether we're talking about an external atom, in which case we'll use the atomic orbital, or whether we're talking about another central atom, in which case we use the hybrid orbital. The second type of bond is the pi bond, which is represented with the lowercase pi. And it results from the side-to-side overlap of unhybridized p orbitals. So Tuesday, we talked about the single bond, the double bond, and the triple bond. A single bond was represented with a single line. A double bond was represented with a double line. And a triple bond was represented with a triple line. Now, the first bond between two atoms will be a single bond. So will be a sigma bond. So a single bond is a sigma bond. But a double bond also has a sigma bond. A triple bond also has a sigma bond because it's the first bond between two atoms. Now, in the case of a double bond, we also have a pi bond. And in the case of a triple bond, we have two pi bonds. So a single bond is strictly a sigma bond, resulting from a direct overlap. A double bond will contain a sigma bond and a pi bond. The sigma bond will be from direct overlap, whereas the pi bond will be from side-to-side overlap of unhybridized p orbitals. And then a triple bond will have a sigma and two pi bonds in it. The sigma bond again will be direct overlap, while the two pi bonds will result from side-to-side overlap of unhybridized p orbitals. So now so we've talked about VSEPR theory, which determines the shape of the molecule. We talked about valence bond theory, which describes the hybridization of the central atom. And within that valence bond theory, I also introduced the concept of sigma and pi bonds. There is one more topic that I said that we would introduce today, and that is molecule polarity. The video I'm going to show you is going to talk briefly about bond polarity, which we will get to on Tuesday, but it spends most of its time on molecule polarity. Now, I want you to watch the video, but then I am going to show you how you can use your electronegativity table to determine the polarity as well.
When the atoms in a covalent bond have different electronegativities, the electrons are shared unequally and the bond is polar. Depending on the molecular shape, polar bonds can give rise to a polar molecule, one with an overall uneven distribution of electron charge. We can see this charge imbalance when the molecules are placed in an electric field. Polarity is a key feature of a molecule because it can influence physical, chemical, and even biological properties. For a diatomic molecule, a polar bond must lead to a polar molecule. Consider hydrogen fluoride, shown here as the Lewis structure changes to a ball and stick model enclosed within the space-filling shape. Note the polar arrows and the colors. If red indicates high electron density and blue indicates low, you can see that the F end of the molecule is much more negative than the H end, and thus HF is highly polar. Between two electric plates with the field off, the molecules lie every which way. With the field on, however, they become oriented with their negative ends facing the positive plate and their positive ends facing the negative plate. If a molecule has more than two atoms, its shape can affect the polarity in a crucial way. For example, in carbon dioxide, since oxygen is more electronegative than carbon, each bond is highly polar. But the linear molecular shape makes the bond polarities cancel each other. So the CO2 molecule is nonpolar. Notice that the orientation of the molecules is random, whether the field is off or on. The situation is very different for water. As in CO2, the highly electronegative oxygen pulls electron density towards itself, so each bond is polar. But the V shape of the molecule allows the bond polarities to reinforce each other, so water is highly polar, as the large polar arrow shows. With the field off, the molecules are oriented randomly, but with it on, their poles become oriented toward the oppositely charged plates. The case of boron trifluoride is similar to that of CO2. Because the three highly polar bonds point to the corners of an equilateral triangle, the bond polarities cancel each other, and BF3 is nonpolar. The molecules are oriented randomly with the field off or on. Like BF3, ammonia has 4 atoms and 3 polar bonds, but the trigonal pyramidal shape means that the bond polarities reinforce each other. Thus, ammonia is highly polar for the same reason that water is. Sometimes two molecules have similar overall shapes, but their slightly different compositions lead to very different polarities. Carbon tetrachloride has 4 polar carbon-chlorine bonds that point to the corners of a tetrahedron, so they cancel each other and give a nonpolar molecule. Substituting a hydrogen for one of the chlorines gives chloroform, another tetrahedral molecule. But now the polar bonds reinforce each other. As a result, chloroform is highly polar. There are even cases when two molecules have similar shapes and identical compositions, but different polarities. Compounds such as cis and trans-dichloroethylene behave this way. Both have the formula C2H2Cl2, and both have trigonal planar shapes around the 2 carbon atoms. Yet, the trans compound is nonpolar because the carbon-chlorine bond polarities cancel each other, while the cis compound is highly polar because they reinforce each other. Since greater polarity leads to stronger attractions among the molecules, the cis compound boils over 18 degrees higher than the trans compound.
Okay. So let's talk about the key points with respect to molecular geometry. First of all, bonds typically have some degree of polarity based on the difference of the electronegativities of the atoms that make up the bond. Page 4 in your handout was the table of electronegativities. What you will notice is fluorine is by far the most electronegative atom, and francium is by far the least electronegative atom on the periodic table, other than helium, neon, and argon, which do not have any type of electronegativity whatsoever. So the bonds typically have some degree of polarity associated with them. The degree we'll talk about on Tuesday, but just for now, they typically have some degree of polarity associated with them. Now, when we start getting into a molecule's polarity, it is based off of on vectors, because that's essentially what these polarities are, is a type of vector. And what we're looking for in order to determine the molecule's polarity is, do the vectors cancel? If it does, then it would be a non-polar molecule. Or are the vectors additive? If so, then it would be a polar molecule. Now, the third thing that came up in that video was what it would be considered to be a dipole moment. And if we break this term apart, we have di, which means two, and we have pole, so two poles. Now, dipole moments are represented with an arrow notation. That arrow, and again, it can be within the bond or it can be within the molecule. It doesn't really matter. We use this arrow notation anytime there's some type of dipole moment. The arrow we use is a normal arrow, but on one end it has cross. The head of the arrow will point towards the more electronegative atom. Whereas the other end of the arrow points towards the less electronegative atom. And when I'm talking about this, we're talking about in a bond. Now, the third thing that you needed to note is that what they gave you was considered to be a density diagram. In the case of the density diagrams that they used, the blue shade represented an area of less density. This is the result of less electronegative atoms. And therefore you wind up with a partial positive end. That partial positive wound up pointing towards the negative electrode. The other thing we had is we had a red shade. And it represented an area of greater electron density. That red area is typically the result of a more electronegative atom. And because there is a greater electron density and electrons are negative, that particular end would be a partial negative end. To the bond or molecule. Since it is partially negative, it would point towards the positive side of a point towards the positive electrode. So let me just illustrate before I give you a bit of a break. I want to illustrate the use of electron geometry and electronegativities to determine the polarity of the molecule. So let's start out with one of the ones that he gave us was water. If I draw water, one way to draw water is the looks like this. Then if I take the electronegativities and I look up the electronegativity table, I would find out that the electronegativity of hydrogen is 2.1. And I would find out that the electronegativity on the oxygen is 3.5. As an overall additive process, what I notice is the electronegativity increase towards the oxygen. Because the electronegativities all increase in one direction, this molecule is polar, and its dipole moment would be in the direction of the oxygen. We can compare that with carbon, with methane. Again, if I look up the electronegativities, hydrogen is a 2.1, whereas carbon is a 2.5. What we see is that there is no trend or no increasing trend in electronegativities. From one side of the molecule to the next. Since there is no trend, this molecule is nonpolar. Okay, it is 3:53. Let's plan to be back at 4 o'clock. And what I will be doing after the break is I will be working with you through some examples from start to finish using the packet that I gave you on Tuesday. We have 7 minutes to kind of chill. Oh dear. I just realized I wasn't talking. Sorry about that. So basically, before I moved on, what I wanted to do is explain the notation that you saw in methane. Molecules are not flat. They are 3D. So we need to have a way to illustrate something that is 3D on a 2D sheet of paper. So we use these different notations for our bonds. A flat line means that the atom is in the same plane as the central atom, whereas a wedge means the atom is coming towards you out of the plane of the central atom. And the dashed means that the atom is going behind the plane of the central atom. So again, we're taking these bonds and we're telling you, are they coming towards you? Are they going away from you? That is what we're trying to demonstrate with these different ways of drawing a bond. So now what we're going to do is I'm actually going to do some examples. And we're going to start with Lewis dot structures and move our way all the way through via CPR theory, where we determine the electron geometry, the molecular geometry, the bond angles. We're going to move into hybridization, where we determine the hybridization of the central atom and the bond type, whether it's pi bond or sigma bond. And finally, we're going to figure out whether these molecules are polar or non-polar. So let's begin with carbon dioxide. Carbon dioxide has 1 carbon and 2 oxygens. Carbon is in group 14. The last digit is a 4, so it has 4 valence electrons. Oxygen is in group 16. The last digit is 6, so it has 6 valence electrons. So carbon contributes 4 and the oxygens contribute 12, giving us a total of 16 valence electrons to distribute. Carbon is always going to be the center of attention. So it is our central atom around which we're going to place our 2 oxygens. Now, the next step in Lewis structures says to draw a single bond between the external atom and the central atom. And we are to subtract 2 for each bond we drew. We drew 2 bonds. 2 times 2 is 4, so we'll subtract out 4 electrons due to the bonds, leaving us 12 left to distribute. The next step says to give your external atoms an octet. To give oxygens an octet, we will need to give each oxygen an additional 6 electrons, which we'll illustrate as dots around those oxygens. By giving our oxygens their octet, we've used up the 12 electrons we had left and we've hit 0. Anytime you hit 0, you ask, does everybody have an octet? Our oxygens do have an octet. They have 6 electrons in the dots and 2 in the bonds. So both of them have an octet. But our carbon currently does not have an octet because it only has 4 valence electrons, because it has only 2 within each of those 2 single bonds. Because a carbon does not have an octet, that means we need to make a multiple bond by sharing a pair of electrons. So we bring in a pair of electrons off of one of our oxygens, and the structure that arises has carbon with a double bond to oxygen and a single bond to oxygen. Because we altered the structure, we asked, does everybody have an octet? The oxygen on the right has an octet. It has 8 valence electrons because it has 6 in the lone pairs and 2 in the single bond. The oxygen on the left also has 8 valence electrons because it has 4 within the double bond and 4 within the lone pairs. But our carbon still only has 6 valence electrons. Since carbon does not have its octet, we are not done in getting the Lewis structure. That means we're going to need to share another pair of electrons, and because chemistry likes symmetry, I'm going to bring them in from the opposite oxygen. So we wind up with carbon that has 2 double bonds, 2 oxygens. And we asked, does everybody have an octet? The left-hand oxygen has 8 valence electrons, 4 within the lone pairs and 4 within the bonds. The the left-hand oxygen has an octet because it has 4 within the lone pairs and 4 within the bonds. But now carbon also has an octet because it has 4 within each of the 2 double bonds. So the Lewis structure for carbon dioxide is this Lewis structure. Now, I'm going to move that Lewis structure down because I'm about to use it for the next part of this process. Okay, so I mentioned earlier that I develop a notation that will help in determining a lot of the pieces of the puzzle. The way I do this is my central atom I'm going to label as A. Each element bonded to that central atom I'm going to label as X. And if there is a lone pair on the central atom, I would label it as N. In this particular case, there is not a lone pair. So my notation is that it is an AX2 molecule, where the number of bonding groups, which is X, plus the number of lone pairs, which is N, would be 2 plus 0 in this case, or in other words, 2. Now, anytime there are only 2 things attached to the central atom, again, anytime there are only 2 things attached to the central atom, they attain minimal repulsion when they are 180 degrees from each other in a linear format. So the electron geometry is linear. And again, it's going to have an ideal bond angle of 180 degrees. Now, because both of these groups are bonding groups, it means that the molecular geometry is also going to be linear. Now, that takes care of determining the electron geometry, it takes care of determining the molecular geometry, and it takes care of determining the ideal bond angle. The next thing we need to do is determine hybridization. And again, that's going to be based off of this number. That number tells you how many atomic orbitals to combine to make the hybrid orbitals. We need to combine two atomic orbitals. So we're going to combine an S and we're going to combine a P. We always start with S, then go to P. So in other words, the hybridization on our central atom is sp hybridized. We can also talk, remember that our structure had two double bonds to oxygen. So we can also talk about our sigma and pi bonds. Basically, we have two carbon double bond oxygens with one sigma and one pi bond each. The last thing we can talk about is our molecule polarity. If you come up with the electronegativities, you would find that oxygen is 3.5 and carbon is 2.5. There is no trend in one direction for the electronegativities. So this molecule is nonpolar. Questions about that particular one? Let's look at another example. Let's look at ammonia. Ammonia has one nitrogen and three hydrogens. Nitrogen is in group 15, the last digit of 5. Hydrogen in group 1, the last digit of 1. The nitrogen contributes 5, the hydrogens contribute 3 for a total of 8 valence electrons. Nitrogen is going to be your central atom because hydrogen can never be, around which we'll surround the nitrogen with hydrogens. We then draw a single bond between the nitrogen and the hydrogens, and we subtract 2 for each bond we drew. We drew 3 bonds, so 3 times 2 is 6, so we'll subtract out 6 electrons due to our bonds, leaving us 2 left to go. The next step says to give your outer atoms an octet. Our hydrogens already have an octet because they only needed 2. And they have 2 within the bonds. But our nitrogen, in order to have an octet, needs the other 2, which we had left over. If you look at it, everybody has an octet. So this is the structure for ammonia. Now we have the nitrogen, which is our central atom A. We have hydrogens, which are bonded to that central atom, which we'll label as X. And we have a lone pair on that central atom. So we have AX3N. From there, we can say X plus N is equal to 3 plus 1. So in other words, we have to have 4 things on the central atom. For 4 things on a central atom, minimal repulsion is obtained when the electron geometry is tetrahedral. A tetrahedral electron geometry means an ideal bond angle of 109.5 degrees. Technically, since ammonia has a lone pair, and lone pairs take up more space, then the bond angle is less than 109.5 degrees. To draw this molecule correctly, we would place the nitrogen and we would place the hydrogens at 3 of the 4 corners of the tetrahedron with a lone pair on the nitrogen. Now, while the electron geometry is tetrahedral, the molecular geometry is based strictly on the bonding groups. And so if we look at these bonds, and we just look at the bonds, what you will see is something that has a triangle, and looks like a pyramid. So it is trigonal pyramidal. Now for the hybridization. We said 4 was the key number. So that means we need 4 atomic orbitals to combine in making the hybrid orbitals. So we're going to take an S, we're going to take 3 P's, and that adds up to 4. So in other words, the hybridization is sp3 hybridized. Nitrogen has been sp3 hybridized. For the bonds, we have 3 nitrogen single bond hydrogen that are sigma bonds. And lastly, for the molecule's polarity, if you look at the table of electronegativities, hydrogen is 2.1, nitrogen is 3.0. Keeping in mind, this is supposed to be based on a triangle up, a trigonal pyramid. It means that there is a trend in the electronegativities towards the nitrogen. So there's a dipole moment. So this is a polar molecule. Questions about that one? Okay, I'm gonna do one more for you, and then I want to show you a few things on Blackboard, and then we will be done. The one I want to do for you now is BRF3. We have 1 bromine, we have 3 fluorines. Bromine is in group 17, last digit of 7, as is fluorine in group 17, last digit of 7. So bromine contributes 7, fluorines contribute 21 for a total of 28 valence electrons to distribute. Bromine is our central atom around which we'll surround it with the fluorines. We're told to draw a single bond between the external atom and the central atom and subtract 2 for every bond we drew. We drew 3 bonds, 3 times 2 is 6, so we'll subtract out 6 electrons. We still have 22 left to go. We're told to give our outer atoms an octet. So to give each fluorine atom its octet, we need to distribute an additional 18 electrons, 6 around each of the fluorines. That still leaves us with 4 valence electrons. When you've given your outer atoms an octet, we're told to place the other electrons on our central atom in pairs. And we hit 0. We ask ourselves, does everybody have an octet? And yes, everybody has an octet. We have our central atom bromine. We have 3 fluorines attached to that central atom. And we have 2 lone pairs on that central atom. Whoa. Keep hitting the wrong thing. So what we have is, we have a molecule that is AX3N2, where X plus N is equal to 3 plus 2, or in other words, we're going to be dealing with 5 things that have to go on the central atom. Minimal repulsion. For 5 things. Is in the trigon, in the electron geometry of trigonal bipyramidal. Now, in drawing something that is trigonal bipyramidal, this is where you have to remember that in trigonal bipyramidal, the lone pairs must go equatorial. So your lone pairs have to go in an equatorial location. Now, if this is trigonal bipyramidal, that means that the ideal bond angle, or in this case, bond angles, is 90 degrees and 120 degrees, because the axial positions are 90 degrees from each other, but the equatorial positions are 120 degrees from each other. So you have both angles there. Now, technically, it is less than the 120 because of the lone pairs and less than 90. So, but that's the ideal bond angle. Now for the molecular geometry. Again, molecular geometry focuses only on the bonding groups. And if you were to look at this geometry, you would see that it is in the form of a T. So it is T-shaped. Now for the hybridization. Again, folks, 5 is the key here. Means you're going to combine 5 atomic orbitals to get the hybrid orbital. So we're going to combine an S, we're going to combine 3 P's, and we're going to combine a D. So the hybridization on our central atom is that it is sp3d hybridized. For our sigma and pi bonds, because they are all single bonds, we have 3 bromine fluorine sigma bonds, because they are all single bonds. Finally, for the polarity, if you look up the electronegativities, fluorine is 4 and bromine is 2.8. Now, this is where it is important to understand that the lone pair takes up more space. So technically, they're not straight up and down on these fluorines. They're more at a slight angle on those fluorines. So when you think about it being at a slight angle, it means that there is an there is a dipole moment towards the fluorines away from the bromine. So this molecule is polar. Questions about that one? Again, folks, your packet helps you walk through each one based off of that notation that I've given you, which helps you a lot along the way. Yes, you do need to be able to draw these molecules. And I will say that if you can memorize how to draw them, how to draw the electron geometry, to go from the electron geometry to the actual molecular geometry, which is what you have to be prepared to draw, all you have to do is replace something that looks like a bond in the electron geometry with a lone pair, and that would get you to the molecular geometry if your molecule has lone pairs. Now, I know that this is a lot to take in. And as I mentioned today, this material is critical that you understand it. So I want to show you just a couple more things on Blackboard. First of all, if you go down to your extra materials, this very last item here, it says VSEPR, etc. video list. If you click on that, what you're going to see is I have videos for 2+ pages of molecules. And they're each individual, so they won't last more than, say, 5-6 minutes typically. This will allow you to watch as many videos as you need in order to get a handle on what I'm describing, but I'm not forcing you to listen to me talk forever and ever and ever if you already have it down. Now, I will say you do have 5 VSEPR Edpuzzle videos, and those 5 VSEPR Edpuzzle videos combine to make one lab grade. So you're stuck watching 5 more. But as far as the rest of these, you can pick and choose what you want from there. Did that show you? I bet it didn't show you. Sorry, I just realized I didn't share my entire screen. Let's try it this way. This is the video list I was talking about that I pulled up when I clicked on it. It's over 2 pages of videos, and you can just click on the YouTube link and it'll take you to the video. But you do have some that you have to do, but these are options for you if you need additional help. The other thing that I wanted to show you is in the optional homework and answer keys. You're always curious how I'm going to ask a question on a test. I'll be blunt with you. The Lewis structures, you're going to have to give me, I will make you draw a Lewis structure. Well, technically a few Lewis structures, but for all of the rest of it, if you look at this VS, VB, etc., I apologize that it's at an angle, but what you're going to see is exactly what you will see on a test. You will be given, for the VSEPR, etc. piece, you will be given a Lewis structure. You will be asked to tell me the shape. You will be asked to tell me the molecular shape. You will be asked to tell me the hybridization. You will be asked to draw the molecule with the correct dipole moment. You will be asked to tell me if it's polar or non-polar. You'll be asked to tell me the ideal bond angle and to tell me the sigma pi bonding description. Each one of these squares is usually 2 points. So that would be 2, 4, 6, 8, 10, 12, somewhere between 14 and 16 points per question set. And you will have 2 or 3 of these on the next test. So again, this gives you some specific practice over some of these molecules, and you're just going to have to pour through them and go through it. But this will give you a specific practice as to what this portion of the exam would look like. So I highly recommend doing it. At least you'll get an idea of what the test will look like. Questions for me?